This PowerPoint goes with the Waves Light and Sound note page. A wave is a disturbance that travels through matter. Think about when you go down to the beach and you see the waves rolling in. What's actually happening is the molecules of the water are moving up and down. The wave itself is moving along and comes down crashing onto the beach. So a wave is a form of energy. Energy travels from one end of the wave to the other. The molecules just move along up and down or side to side as a wave travels through. The medium is the actual matter through which the wave travels. Mediums are usually solids, liquids, and gases. Some types of waves, such as an electromagnetic wave, can travel through empty space. We have electromagnetic waves that come from the sun. We have infrared radiation. We have visible light. We have gamma radiation. These things come from the sun to us and they travel through empty space. We have two types of waves. First type of wave is a transverse wave. It's a disturbance that moves the medium at right angles to the direction in which the energy travels. So as I said previously, energy moves from one end of the wave all the way to the other. Just think of a water wave. Water waves start miles offshore. The energy of the wave keeps going, keeps going, keeps going until it crashes onto the beach. But the actual water molecules itself, they just go up and down. Also think about a stadium wave. That's another example of a transverse wave. If you're at Yankee Stadium or if you're at Met Stadium and they have a wave that's moving around the stadium, the people, they're just moving their arms up and down. But the actual energy of the wave moves around the stadium. So if you're moving your arms up and down, but the energy is moving across, that's where we get the right angle. The second type of wave we have is a longitudinal wave. And in this case, it's a disturbance that moves the medium in the same direction as the energy of the wave. I want you to think of a field of wheat blowing in the wind. As the wind blows, the field of wheat moves sideways. When the wind starts to slow down or stops, the wheat bounces back up again. The wind blows, it moves sideways, so on and so forth. That's an example of a longitudinal wave. Sound waves are also longitudinal waves. They're compressional waves, and they move along that same fashion. Here are some examples of transverse and longitudinal waves. A water wave, like this pond, that's a transverse wave. Right underneath it, we have the electromagnetic spectrum, which we're going to spend some time talking about in another video. That is also a transverse wave. Then on the right, we have a sound wave. That's considered a longitudinal wave. And the same thing with that spring underneath. That is also considered a longitudinal wave. If you go look at this presentation on my webpage, you can actually see the PowerPoint where these links and these videos are much more active than they are right now.
So what we have here is a longitudinal wave. What you can see is there are areas where the particles are squished together. Those are the areas of compression. So in the model here, we have two compressions that are moving along to the right, and in between there's an area where it's kind of spread out. I want you to think of a slinky. When it comes together, it moves apart, comes together, moves apart. That's like a longitudinal wave. I also want you to notice these two red arrows over on the left. They are highlighting two different particles. And if you notice, those particles only move side to side, but the wave itself moves along to the right. That part represents the wave's energy. The energy moves from the left to the right and all the way through. Whereas those two red dots with the arrows and then the two other red dots, those particles are just moving back and forth. So here we have a transverse wave. In the longitudinal wave, it was kind of straight across like this, and the waves are moving compressionally. Now you can see that the molecules are actually moving up and down. So the molecules are moving up and down, while the energy of the wave is moving across this way. There's your 90-degree angle that the molecules move comparison to the wave's energy.
So as I said earlier, the molecules themselves in a transverse wave are moving up and down. The molecules in a longitudinal wave are just moving side to side. So what is actually traveling from one end of the wave all the way to the other? Well, think about when you're at the ocean and you're standing in front of that big wave. That big wave that has this power or this energy that's going to knock you down. So that's really what's traveling from one end of the wave all the way to the other. So just to recap, waves transfer energy through a medium, and when you get hit by a wave, you're actually getting hit by that energy. So it just so happens, I said earlier, waves do start many miles or kilometers offshore, usually from some kind of wind out in the ocean, and then that energy just keeps going all the way through. Now we have this, which is called characteristics of waves. They're really different parts of the waves, but they'll be known as characteristics. So the first characteristic that we have is the crest of the wave. Crest refers to the topmost portion. Then we have what is called the rest, or we like to say that the baseline. Think about the bay when it's like glass. It's perfectly flat. That's what we consider the rest. Then we have the trough. The trough is the lowest part of the wave. I like to think of like farm animals eat out of a trough. The trough is curved. It holds their food, so it's shaped like a bowl. So when you look at this, think of the farm animals eating out of a trough, how it's bowl-shaped. Then we have the amplitude. Now the amplitude is the height of the wave. It's measured from the rest to the crest. That's where our waves get our energy. Now think about that for a moment. I'll go back to this example at the ocean. If you get hit by a wave that's only 2 feet high, nothing much will happen. But now let's say we change the amplitude of that wave. We make it a 6-foot wave. What's going to happen as that wave starts to hit you now? Well, that wave is definitely packing a lot more energy, so you will definitely get knocked over. The higher the wave, the more energy that you have. Then lastly, we have the wave length. It's literally measuring the length of the wave. It's measured from the crest of one wave to the identical spot on the next wave. So from crest to crest, or it can be measured from trough to trough. Whatever part you're starting on one wave, its measure is the counterpart on the next wave, same spot. So we're going to dive into frequency and wave speed. This first one here, frequency, this is going to be some extra credit down at the bottom. The same thing with the wave speed. You can answer those questions down below, press submit if you're in the Google Doc, and then you'll get some extra credit for this portion of the program. So frequency is the number of waves that pass a point in 1 second, and we measure it in a unit called hertz. Now, I like you to think of frequency in this way. Think about how many times you go to McDonald's, how frequently you go to McDonald's. You may go once a month, you could go once a week, you could go twice a week. Usually it's a number of times that correspond with some amount of time that has passed. So it's how often you go in a certain amount of time. So here, when we talk about wave frequency, we're going to talk about the amount or quantity of waves that pass in a given amount of time, which is going to be 1 second. So wave speed has 2 formulas. We can use distance the wave travels divided by the time, which is pretty much the same formula as speed, which is distance divided by time. But we like to use frequency times wavelength. So we just talked about frequency, which is measured in hertz, times wavelength, which is the length of the wave, which is going to be measured in meters. So once again, there's some sample problems down below. You try those problems and click submit. If you get them all right, I'll give you some extra credit. So it's frequency times wavelength, and frequency is measured in hertz, and wavelength is measured in meters.